Scientific evidence points to the fact that consciousness emerges from the neural activities in the brain. Many neuroscientific studies have found that brain activity increases when we encounter novel or unexpected events and decreases when the events become predictable or repetitive. This is called repetition suppression. The brain's ability to predict is facilitated by top-down neural activities. To elaborate, consider the following scenario. You are taking an exam and you are asked to answer 16 true and false questions. However, you find that none of the questions make sense to you. What will you do in this case? Maybe you toss a coin and randomly select true or false for each question. The teacher marks your answer and you get 8/16. The teacher now gives the class another try on the same questions. You change your answers again randomly. This time your score is 7/16. The teacher gives you another try and says you are allowed to try again 20 times. Your task is to learn from your past trials and try to reach the total score of 16 in less than 20 trials. If you follow your current approach, it may take you 65,000 trials, more or less depending on your luck. If you are into programming, you can simulate that easily in Python as follows. First, import numpy, then define a check score function to compare your guess with the truth. Generate a true and false pattern to simulate the questions. In the brute force approach, you guess randomly and repeatedly until you score 16. In this case, we get the right answer after more than 80,000 trials. To make it easier to think about the solution, I made this online game. You can find the link in the description. Your task is to predict the hidden true and false answers without hitting the reveal button. You can toggle your answers and peek at your score each time by hitting the check score button. See if you can get the full mark in less than 20 trials without hitting the reveal button. I'll explain the relevance of this task to our topic, but first let us know how you would solve this task. Okay, I assume you already tried it and now you want to hear the answer. There are several ways to tackle this problem. The easiest can be hinted from biology by trying point mutations. Make any guess and check your initial score. Then mutate one guess at a time and recheck your score each time. If the score increases, it means you made a correct step. If not, it means you made an incorrect step. With this approach, you are guaranteed to reach a total score of 16 in 16 trials. Now you know how to pass this exam. But let's say there is a big prize for anyone finding the answer with a minimum number of trials. This makes sense because we live in a competitive world. Let's say that the teacher gives us as much time as you require between each trial. You could spend hours or days thinking about it. You can even use whatever computational facility at your hand. The only requirement is that you reach the perfect score in a minimal number of trials. In this case, what's your approach? You may say this is a contrived exam, because exams are tests for knowledge and we usually get detailed supervision to differentiate right from wrong. But that's not always the case in real life. We are spoon-fed for a short period of our life, but the rest of our life is unsupervised. We usually only get a total score for our performance but without details. Most of the feedback we get is a total assessment of our work as a whole package. And as you become top in your field, it will become harder to get specific guidance. At that point, everyone can judge you, but no one can help you. You have to discover the details from your repeated trials and errors guided by the general feedback. This is why this simple toy game is representative for many aspects of our life, and trying to find an optimal solution can give us a lot of insight. Uncovering the hidden pattern from the total score is an inverse problem. Unlike the forward problem, where it's easy to find a unique answer, inverse problems are tricky because there is no unique answer. For example, if they asked you, "What is this?" you can unambiguously answer, "It's a door." But if a customer asked you to build a door, you can't know what door type your customer wants. But if you have prior knowledge of what customers usually like, this will help you to pin down the correct answer. Likewise, in the previous problem, if you get additional hints, you can figure out the solution with no confusion. If you have prior knowledge about someone's political affiliation or what makes them happy or sad, then you can pin down the part of the video that was meant by the comment even if it was non-specific. Finding the right hints is an art by itself. I remember from our med school days we used to ask the patient countless questions to pin down the diagnosis, while a senior doctor could reach the same diagnosis with fewer questions, because he already has the proper prior knowledge to focus on what matters and exclude non-important questions. This applies to our game too. If from our prior beliefs you knew your teacher likes to alternate the pattern, you can pin down the possible answers and eliminate a lot of candidates from your search space. You can think of your prior knowledge as higher level neurons that store the weights of your memories and your pre-existing beliefs and biases in its connections. The problem is, in our game, we use random patterns and have no prior knowledge. Therefore, we need to start from scratch and develop our knowledge trial by trial efficiently. To do so, let's formulate this as an optimization problem. First, we change the true and false guesses to a range of 0 to 1, where 0 is false and 1 is true. Then x's are our guesses, y's are our corresponding scores, and weights are the pattern to be guessed. We can represent them as the following linear equation. The dot product between the guesses and the weight vector is equal to the scores. Python has convenient algebra methods which can let us to find the weights in a couple lines of code. Here's the complete Python code if you like to follow along. Although our scoring was non-linear, because of simplicity we were still able to solve this using linear regression. But to solve this, we still needed 16 different guess vectors, which correspond to 16 different trials. But now we have formulated this as an optimization problem. Hence we can experiment with the guesses and try to reach the truth in fewer trials. Let's take a simple grid of 4 questions. Any square has 50% chance to be true or false. There are 16 possible patterns. If we initially set all of them to false and the score was 2, it means there are 2 truths, and we can eliminate all the patterns that have more or less than 2 truths. Now we can either mutate one score at a time like before, or be adventurous and mutate 2 squares at once. If the score increases or decreases by 2, we can immediately spot the answer. But if we are unlucky, the score remains the same, meaning the hidden pattern is among the remaining 4 grids. Again, we can mutate 2 squares, and if the score increases or decreases by 2, we can spot the answer. If not, we can exclude these 2. The truth now is between the last 2 patterns. Now, if we are without a good memory capacity, we achieved nothing with our previous guesses because the probability of finding true or false under each square is still 50%. That's why point mutations work better for DNA-based adaptations, but they are trial-wise inefficient. Since we have memory, we gained a lot of knowledge about the underlying pattern from our past guesses. Now we only need to switch any one of these squares and all our uncertainties will collapse to one truth. Now we know with double mutations we can gain more information with each trial, but this requires more memory and compute. The problem is, as we mutate more guesses at once, it will become harder to track all the possibilities. Unlike our long-term memory, our working memory has a very limited capacity. If you try to hold more than 7 elements in your head at once, the older ones fades away. To overcome this limitation, humans invented writing. That's why writing and civilization emerged together, because writing expanded our working memory. Today, we have better tools, so let's exploit them and write our thoughts into an algorithm. This part can be a bit boring, but hold on a bit. If we start guessing all false, from the initial score we can estimate the total truths and falses like this, but we don't know how they are distributed on the grid. In the next trial, if we switch the right side to true from the updated score, and with some math, we can figure out how many truths are there on each side. Using the method we described before, we can put these findings into a matrix and compute the probabilities of where to find the truths. We can repeat this for any additional guesses, and with each guess we will get more precise probabilities on where the truths are located. Because when we intersect the guesses together, we will get more information on how the updated scores relate to each partition. So now we have modified our game so that with each guess, it will give us the updated probabilities of where the truths are located. Let's see how many trials we need to reach the perfect score. In this example, we got an initial score of 15. That means there is only one true hidden answer in this entire grid. Next, we switch half of the grid to true. From the updated probabilities, we know the hidden true is not on the right side. Let's subdivide this part into 2 partitions, and let's follow the evidence and do that for the remaining parts. We located the true with confidence in 4 trials. This approach has a logarithmic complexity, meaning that for a grid size of 1,000,000 squares, you only need 20 trials to locate where is the true square. In this next example, we get a score of 14, meaning 2 true answers are hiding in this grid. This is trickier than the first example, especially if the true answers are not located close to each other. In this case, we need to explore more partitions to locate both of them. One simple and general approach is to switch half of the squares to true in various frequencies. Think of them as square sine waves. This can capture the regularities in the data. It also makes sense as a prior because in our world, most patterns are spatially regular and coherent. This is why Fourier transform methods are useful for compressing visual and audio data. I may be stretching here, but our brain has rhythmic waves with various frequencies, and grid cells also follow a similar pattern. The problem is, in our game we use random patterns to make guessing deliberately more difficult. This is why after these few guesses we still can't reach 100% confidence levels on where the truths are located. At this stage, we can make some leap of faith and follow the evidence. Whenever we see high probability, we switch them to true, and whenever we see low probability, we switch them to false. We submit this new guess and the evidence gets updated. If the new score is still not perfect, we again follow the new evidence and repeat until we reach the perfect score. Let's simulate that for 100 random patterns. Putting everything we discussed together and running the simulations, we see the average performance is around 11. Looking at the individual performances, we see that most patterns were predicted in less than 16 trials. However, we can spot several patterns reaching the maximum allowed trials of 20, meaning our approach couldn't find the solution for these patterns. So why this happens? Let's examine one of these hard to predict patterns. As I said, when we follow the evidence, we are making some leaps of faith. Because even though if a square is 80% true, it's also 20% false. Although following the direction of higher evidence seems optimal, but if the evidence is not perfect, chances that we misjudge some places. That's not an issue if the updated evidence keeps pointing to better patterns. However, in some cases, such as this one, the updated evidence points to the same pattern as before, even though the perfect score is not reached. In optimization, this is known as the local maxima trap. Imagine your task is to reach the highest peak, but your sight is limited. You see higher ground levels on your right side. You follow the local evidence, and at some point you reach the peak. Your global score is still not perfect, but the local evidence keeps pointing to this place as the highest. If your expectation is low, that's fine, you can live a comfortable, happy life there. If not, then shake your beliefs and leave your comfort zone. Look somewhere else and hopefully you may find new evidence that leads you to a higher peak. Okay, now let's translate this influential talk to code. The easiest way is whenever the pattern traps make some random disturbance in the establishment, then rescore. Hopefully the new evidence is released from the trap and points you to a new direction. Let's add this naive solution to our code. Now the average trial is around 9 and there is no entrapment as all the individual simulations were solved in less than 16 trials. Also remember that we used random patterns to make our task more challenging. In our life, patterns are spatially regular and more coherent. If we use such regular patterns, we can guess them in even fewer trials. Not only that, in reality, patterns are also temporally regular, some repeating more than others. This is where the importance of our long-term memory comes, because it can store frequent and important patterns. This will reduce the search space hugely when we need to predict a memorized pattern. Games like Wordle rely on long-term memory to search for the answer, but the solution for our game is not memorized. Therefore, we are computing the solution from scratch. Long-term memory is very important for our survival and is more integrated with our top-down processes. It also gets a lot of dopamine and has the nostalgia element. This is why more people enjoy memory games over math-intensive games. But not every important pattern can be memorized. For example, some patterns are far away and some are happening over very long periods beyond our lifespan. So far we talked about the feedback that's coming in the form of a global score. However, feedback can come from our senses too. Our senses can be augmented with various tools. We can think of the information coming up from our senses as the ground truth, while the information coming down from our beliefs is our guess for the truth. The mismatch between these two is the prediction error. This is what our brain tries to minimize according to the predictive coding theories. In other words, the match between these two signals is the score that our brain tries to maximize efficiently. That's what we were trying to achieve in our simulations. Now you might ask, what's the point of the top-down prediction if we still need to rely on the bottom-up information? We can detect the world and then act accordingly. Well, the world we live in is dangerous and competitive. By the time you detect the danger, it's already too late. So you have to predict or at least detect quickly. In the top-down prediction, the information about the world comes from our beliefs, not from our senses. And this is what makes us quick and trial-wise efficient. Here is a fun experiment. Hold a paper in front of you and draw a large dot on both sides. Close your right eye and look at the right dot with your left eye. Gradually move the paper away. At some point you should see the left dot disappearing completely. This is because of a blind spot in our eye. There is a part of our vision that's completely lacking the sensory input. Yet we don't feel that because our brain fills the gap for us. In fact, at any time, you are only getting detailed information from a small part of our vision. Because your eye moves continually around, your brain gets enough information to fill all the gaps for you. This is why in the dark you start to see shapes, because your brain doesn't get enough updates from the bottom-up systems. So the top-up system fills up the gap according to your belief and the context. But that's not a drawback. In fact, that's what makes your brain fast and sample efficient. Let's say someone asked you to guess a word behind this grid. Without the top-down process, you are out of context. Even if they reveal the first letter, the search space is still huge. But let's say you were in a zoo, or for whatever reason you thought the word is most likely lion. You would expect the first letter to be L. If they reveal the first letter and it matched your expectation, then that could be enough to assume the word is indeed lion and move on to the next word without checking the remaining letters. If you are not confident enough, you might ask for a second letter just to become more confident. If you are expecting Lion King, you only need to pick the first letter of the next word. If it matched with your prediction, you can move on again to the next word directly. The more your predictions match with the data, the more confident your brain gets. Hence, you can speed up and skip more letters. This is why we can read and understand this text despite so many errors, because you are reading from your top-down predictions. Even with few samples, your findings are significant because they are not post hoc findings. And that's what makes us fast to detect things and make us capable to understand each other with minimal gestures. This is why robots seem less interactive and less lively, because today's AI and machine learning products are largely bottom-up systems. Despite the amazing results from deep learning recently, compared to our brain, they are still very inefficient sample-wise. They need to read and memorize the entire Wikipedia to become proficient in writing. Self-driving cars make countless mistakes in their simulated environments just to learn to drive safely. In contrast, humans learn to drive with fewer mistakes because we can integrate the novel tasks with our prior knowledge efficiently. The top-down process gives you the bird's eye view of your local world and the feeling of agency, where to look and where to sample. We live inside our beliefs most of the time. The bottom-up sensory feedback is only needed to update our beliefs or to recontextualize us if we mispredict. When we are confident, we don't need to process too much information. Therefore, we sample less from our senses. In contrast, when we are doubtful, we need to sample more and our brain needs to process more. Now you can understand why more activity is recorded from our brain when we face something novel or unexpected, and vice versa. In one of our studies, we used functional MRI on 2 different datasets to test several repetition models. And the meaning model indeed suggested that the neural firing rate reduces near the site of the repeated stimuli. Complementary studies also found similar results for the expected stimuli. These findings link back nicely with the established predictive coding literature in neuroscience. I think we can correlate these findings to our subjective feelings. When the first time you learn to drive, you are overwhelmed with the novel environment. You feel more self-conscious with your actions. As things become repetitive and predictable, they become part of your implicit memories, and you can handle the gear subconsciously. It's obvious that when things around us become too predictable, they become too boring and we get sleepy. On the other hand, too much noise can also make us uninterested. What makes us more alert is the edge of uncertainty, like a horror movie where we think we can predict but it keeps surprising us. Think about the never-ending surprises of a tense World Cup final or a predictable chess game that surprises us. Your life is a tree of choices. The farther it gets away, the more branches it gets and less predictable it becomes. You are conscious where it matters. At the edge of unpredictability is where you live most of your conscious life. It is the intersection of chaos and order. It's where new solutions can be found, and it's where your search is meaningful. Despite all the virtues, our brain has its shortcomings too due to the biological inconveniences. The signal passage is low, too much energy is spent on support and waste removal, memory capacity is limited, and more importantly, our short lifespan doesn't let us to learn everything. This is why we specialize to reach the edge of knowledge and discover new things. But specializations leads to local maxima traps. That's why we need to collaborate to share knowledge. But our communication is not so efficient. Today you think you will hang out with your friend, but your friend have other plans. If you knew that sooner, you wouldn't have wasted too much time and moved on to spend your conscious thoughts elsewhere. Galactus and Dr. Manhattan don't have such problems because they can process global information and hence they can predict very far into future. For example, Galactus can see all the possible outcomes far ahead, and because he is very powerful, he is confident that he can choose the path he wants and prune all the other unwanted branches. If he lives through this predictable path consciously, with no thrill, no surprise, he will get severe depression, because it's like living in a solitary prison. Alternatively, he can sleep his way through, as he can deal with these slight inconveniences subconsciously with his implicit memories. Only when he faces a real challenge, the future outcomes becomes uncertain again. This is where he needs to wake up to process more sensory information and act more consciously. So even though these guys can live for billion years, it feels like few years for them. I used to hate hardship and life's difficulties. I was looking for an easy shortcut to bypass all the hustle, to reach the state of no more doubts and no more confusion. But now I realized doubt is what makes us conscious, because that's what drives us to seek knowledge and worth living. By the way, I am Huner. There are some topics thrills me to make videos about, so if you liked this one, chances that you like the next one. Please consider subscribing or watching my other videos. Thanks for staying, best wishes and Happy New Year.